Hello, we are Team 40, and our project was on the design of a strand burner. We are a team of 4 mechanical engineering students. My name is Kyle McDougall.
My name is Akarsh Shivastav, and I'm a senior majoring in mechanical engineering.
Hi, my name is Michael Boris.
And last but not the least, my name is Kancham Patel.
The goal of this project was to complete the construction of a strand burner. A strand burner is a device that takes a small piece of solid rocket propellant and burns it, simulating the effects of being inside a rocket motor. By using this device, burn rates can be determined and the rocket motor can be designed.
We are assigned the task of connecting the nitrogen tank to the strand burner and then venting the hazardous gases into the fume hood. There are emergency ventilations added in the plumbing to reduce the risk of failure and increase the safety of the operator.
The electrical wiring was completely sketched out and drafted while keeping in mind the chronology of power, optic carriers, and safety. We drew AC power from a wall outlet to power 3 relays: the emergency, inlet, and vent relay. These relays acted as switches that controlled the respective valves and the optic carriers for the emergency inlet and outlet functions. A DC power supply was also integrated into the circuit that powered the optic carriers, which transmit the readings to and from the DAC board. The DAC board powers the photodiode attachment as well as receives readings from it. Lastly, the panel meter powers our pressure transducer. In the end, all the attachments and components that received or distributed any significant electric current were then safely grounded.
During the process of finalizing the strand burner, attachments had to be made that were not thought about when first designing the strand burner.
The main goal of our project was to design a functioning code that any user can easily use. This code must have a simple interface and be able to control the strand burner with as little human interaction as possible during the testing time. This code will also have safety features in case of an emergency.
Our initial plan was to use Arduino and Python to create a code that can analyze and export temperature and pressure readings. However, since our sponsor wanted the results and code to run in LabVIEW, the team decided to switch over to the specified coding platform. For the power supply, initially, the electric power was not enough for the strand burner to be able to efficiently ignite the rocket propellant and simultaneously export pressure transducer and photodiode readings. To rectify this error, we used a transformer to satisfy the power requirement. We had to decide on how we wanted to observe the burn rate because an internal recording device such as a GoPro did not seem feasible. The brightness measured from the photodiode would give us a far better understanding of the burn rate, and hence we decided on using a photodiode attachment. Before testing, we realized that an alternative evacuation system for the gases and burn propellant needs to be integrated in order to prevent reverse flow and potential damage to the equipment.
Another design that we had to make for the strand burner was the ventilation stand. This was built out of 3 pieces of unistrut bar to make sure the ventilation tubing does not vibrate inside of the fume hood when it is ventilating the remaining high pressurized gases out of the system.
This attachment was designed to make sure the photodiode will be secured to the strand burner. It is also important that this attachment will keep all light outside of the chamber. If light were to reach inside the chamber, it will ruin the data that was collected. When the user is ready to test, the start button can be pressed. When pressed, current will be sent to the inlet valve, opening the valve. This will let nitrogen gas fill into the chamber at a set pressure. After a set amount of time that was predetermined by the time to fill tank setting, current will stop and the valve will close. This locks the pressurized gas into the chamber. When the propellant is filled to correct pressure and all valves are closed, the ignite button can be pressed. This will send current to the nichrome wire. The current continues to flow for a set amount of time that is determined by the time to ignite setting, or until the propellant burns. When pressing ignite, the time to ignite delay will start, followed by data collection of pressure and brightness. When the propellant is fully burned, the vent button can be pressed. This will send current to the vent valve, and the valve will open, releasing hazardous gases into the fume hood. When all the gases are vented and testing is done, the stop button can be pressed. This will take current away from all the valves and restart the data. There is an emergency button. When pressed, it will take current away from all the valves, which will open both the vent and the emergency valve and close the inlet valve. This is done to vent any hazardous gas into the fume hood and release any pressure buildup in the system. This button should be pressed if some tubing has been clogged or if the experiment needs to suddenly stop.
The last function on the interface that is located to the left of the Save to function gives the user a live update of the pressure inside of the chamber at all times to show the user when the chamber is up to specific testing pressures, as well as live updates of the brightness inside of the chamber to indicate when the propellant is ignited and when it is finished. The arrows to the left let the user switch between the pressure channel and the brightness channel. A few other functions on the interface that we added to make it easier for the user to change before starting the experiment are Save to File. This is located towards the bottom middle, and this part of the interface lets you select a location on your computer where the code will send all the data in a text file. This coding feature has a design so that the data will be put into two columns. The first column will show time in seconds, and the second column will show the voltage coming from the photodiode to tell us the brightness inside the chamber during the test. The code was also designed to make the file name titled with the date and as well as the hour, minute, and second of the day the test started at. Towards the bottom left of the interface, the function tank fill time lets the user manually select how long it will let the system fill with nitrogen gas, and this is in seconds. And to the right is data collection time, and this lets the user select a time frame for how long the code will collect data in milliseconds during the data collection period. The next one to the right is time to ignite, and this lets the user select how long it will send power to the ignition for igniting in seconds. The last function to the right is time to ignite delay, and this lets the user select the delay for when the igniting will occur after pressing the ignite button. This is also in seconds.
To understand the code, the valves must be understood. For the inlet valve, we use a normally closed solenoid valve. This means that the valve will always be closed until current passes through it. The vent and the emergency valve are both normally open solenoid valves, meaning they are always open until current passes through them. Having the vent valves normally open was done on purpose for safety. If an experiment is being done and the power goes out, the valve will automatically open, releasing any hazardous gas into the fume hood.
To verify all the functions of the Strand burner were being carried out in an autonomous, efficient, and synchronized manner, the team decided to perform a dry test which would serve as our proof of concept. The following operations were performed to authenticate all the working components of the device. Draw power and check if all meters and indicators on the lab view were displaying initial values. Give values command to open and check airflow and pressure readings. Flash photodiode attachment with bright light to verify that it can capture brightness intensity. Hit start to begin the program and create save files to export results. Hit ignite switch and check if live wire is ready to ignite propellant. Hit emergency to test backup evaluation system. Hit stop. View results and verify date, time, tabulated data format. We didn't like to make any purchase as the organization of AIAA and our sponsor Dr. Lynch had all the tools and supplies we needed. But we would like to order a photodiode that Dr. Lynch recommended for us to use for the Strand burner so we could return the photodiode that Dr. Lynch let us borrow for the meantime. Dr. Lynch provided us NI-USB 6003 digital acquisition multifunctional I/O device. We have summarized the amount of labor and hours per member in the bottom right under engineering labor. We are able to successfully meet the sponsor's expectation of creating a Strand burner that is able to ignite a piece of propellant while analyzing and exporting the burn rate and pressure readings. These readings are exported into a tabulated and graphical format through the coding platform LabVIEW. After a dry test of the strand burner and verification of the functionality of all components, checking the readings from the photodiode and pressure transducer, and verifying the exported results on the LabVIEW, the strand burner was deemed completed and was set up for any testing in the future. The importance of measuring burn rates of any mixture of propellant is incomparable, as it deems to be extremely useful to our sponsor, AIAA. They can use this strand burner to determine what mixture of propellant give the best results for rockets being entered into competitions held by organizations like the National Association of Rocketry and SpaceX, as well as for any educational or experimental purposes.
We would like to extend our gratitude to the student organization AIAA for providing the guidance, knowledge, and support we needed to complete this project. Their resources and knowledge proved to be the catalyst required for the success of this project, not only by supplying the components needed, but also by being a strong foundation to rely upon when overcome by challenges. We would also like to thank Gary Crawford, who leads the machine shop, for helping us fabricate all the attachments and components needed for the strand burner. Lastly, we are greatly indebted to Mr. Atif Yardimchi for being the pace setter and driving force that aided us in overcoming all the hurdles we faced throughout this project. Special thanks to Dr. Patrick Lynch, whose guidance, resources, and unparalleled knowledge about LabVIEW unequivocally led the team to create a successful code for the device. Not only do we appreciate his expertise, we also wanted to acknowledge his contribution of providing the team with all necessary components and parts as needed throughout the course of this project. We are obliged to all our sponsors for their invaluable contributions.